Reality isn't what you think it is right now. As you watch this video, you're probably sitting somewhere solid, maybe on a chair, maybe on a couch. The screen in front of you feels real. The light hitting your eyes feels predictable. One moment follows the next in a way that makes sense. But what if I told you that beneath all of this apparent solidity lies something so profoundly strange that it has kept the greatest minds in physics at arguing for over a century, not because they're confused about the math works perfectly, but because they fundamentally cannot agree on what the math actually means about the nature of reality itself. Welcome to the world of quantum paradoxes. These aren't just clever thought experiments or mathematical curiosities. These are verified experimental results that suggest our entire understanding of how the universe works might be fundamentally incomplete, or worse, fundamentally wrong. Richard Feynman, one of the most brilliant physicists of the 20th century, once said, "I think I can safely say that nobody understands quantum mechanics. If that doesn't unsettle you, it should. Because the implications of what we're about to explore aren't just strange, they're terrifying in their implications for what we think we know about existence itself." Let's start with something simple. Hold up your hand. Look at it. It's there, right? It exists whether you're looking at it or not. At least, that's what common sense tells you. That's what centuries of classical physics assumed. Objects have properties, position, velocity, color, mass, that exist independently of whether anyone is measuring them. This worldview served humanity incredibly well. Newton's laws predicted planetary motion. Engineers built bridges and machines. Einstein refined our understanding with relativity, showing that space and time are intertwined. But even in his universe, things still had definite properties. The moon existed even when nobody was looking at it. Then came quantum mechanics. In the early 20th century, scientists began studying the behavior of atoms, electrons, and photons, the smallest building blocks of matter and light. And immediately they noticed something was off. These tiny particles didn't behave like miniature billiard balls. They behaved in ways that seemed to violate every intuition we had about how reality works. They discovered that particles don't have definite positions or velocities until you measure them. Before measurement, they exist in what's called a superposition, a state where they are simultaneously in multiple states at once. It's not that we don't know which state they're in, it's that they literally are in all possible states simultaneously. The mathematics describing this behavior, quantum mechanics, turned out to be stunningly accurate. It's been tested to over 10 decimal places in some experiments, making it the most precisely verified theory in the history of science. Modern technology depends on it. Your smartphone, GPS, MRI machines, lasers, computer chips. None of these would exist without quantum mechanics. But here's the terrifying part. Despite this incredible predictive power, we still don't know what quantum mechanics is actually telling us about reality. Is it describing something real about the universe? Or is it just a mathematical tool that happens to give correct predictions? And when we try to interpret what these equations mean, when we try to bridge the gap between the quantum description and our everyday experience, we run headfirst into paradoxes that seem to shatter our most basic assumptions about time, causality, and the nature of existence itself. To understand how deep this problem goes, we need to look at what's arguably the most important experiment in quantum physics: the double-slit experiment. It's simple to set up, but its implications are profound. Take a barrier with two narrow slits cut into it. Behind it, place a detection screen. Now fire particles. Let's use electrons at the barrier. What do you see? If electrons were simply tiny balls, you'd expect to see two bright bands on the screen, corresponding to electrons that pass through each slit. That's what classical physics predicts. That's what common sense says should happen, but that's not what we observe. Instead, we see an interference pattern, multiple alternating bright and dark bands spread across the screen. This is the signature of waves, not particles. When waves pass through two slits, they spread out and overlap, creating regions where they reinforce each other, bright bands, and regions where they cancel out, dark bands. This is already strange, but it gets stranger. This interference pattern appears even when you fire electrons one at a time. Each individual electron somehow passes through both slits simultaneously, interfering with itself to create the wave pattern. Think about what this means. A single, indivisible electron doesn't choose one slit or the other. It exists in a superposition, passing through both slits at the same time, and only after passing through both does it interfere with itself to determine where it lands on the screen. Now here's where it becomes truly bizarre. If you place detectors at the slits to determine which slit each electron passes through, the interference pattern vanishes, the wave-like behavior disappears, and you get exactly what classical physics predicts. Two bright bands as if the electron passed through just one. Slit, the act of measurement, the act of trying to determine which path the electron took, fundamentally changes the outcome of the experiment. When you're not watching, the electron behaves like a wave passing through both slits. When you're watching, it behaves like a particle going through one slit. It's as if the electron knows whether you're observing it or not, and changes its behavior accordingly. This experiment has been repeated countless times with electrons, photons, atoms, and even large molecules containing thousands of atoms. In 2019, physicists successfully demonstrated interference with molecules made of 2000 atoms. These aren't microscopic quantum objects anymore. They're approaching sizes visible under an optical microscope. The boundary between the quantum world and the classical world isn't where we thought it was. It might not exist at all. The implications are staggering. If measurement fundamentally alters reality, then what is reality when nothing is measuring it? Does the universe exist in a definite state, or is it a hazy cloud of possibilities that only crystallizes into certainty when observed? This brings us to what physicists call the measurement problem, arguably the deepest unresolved issue in quantum mechanics. Before you measure a quantum system, it exists in superposition. The mathematics describes it using something called a wave function, a mathematical object that encodes all possible states the system could be in, along with the probability of finding it in each state. When you measure the system, you get one definite result. The electron is here, not there. The photon is polarized vertically, not horizontally. The wave function collapses from many possibilities to one actuality. But what exactly causes this collapse? What counts as a measurement? Does the measuring device need to be conscious? Can a machine perform a measurement, or does it require a human observer? Does the universe somehow know when it's being measured? These might sound like philosophical questions, but they have real experimental consequences, and physicists are deeply divided on the answers. The traditional explanation is called the Copenhagen interpretation, developed in the 1920s primarily by Niels Bohr and Werner Heisenberg. According to this view, the wave function is just a mathematical tool for calculating probabilities. It doesn't represent anything physically real. When you measure a quantum system, you're not collapsing some physical thing, you're simply updating your knowledge about what state the system is in. But this explanation has a glaring problem. It requires a fundamental distinction between the quantum world, which exists in superposition, and the classical world, which is definite. Where is the boundary? When does a system become classical enough that it stops being in superposition? There is no clear answer, and this bothered many physicists, including Einstein. He famously asked, "Does the moon exist only when I look at it?" If quantum mechanics is universal, if it applies to everything, then technically even, the moon should be in superposition when unobserved. But that seems absurd. Erwin Schrödinger, one of the founders of quantum mechanics, created a thought experiment to highlight this absurdity. Place a cat in a sealed box with a vial of poison connected to a radioactive atom. If the atom decays, the poison is released and the cat dies. If it doesn't decay, the cat lives. Radioactive decay is a quantum event. So according to quantum mechanics, before you open the box, the atom exists in superposition, both decayed and not decayed, which means the cat must also exist in superposition simultaneously dead and alive. This seems ridiculous. Cats are either alive or dead, not both. But if quantum mechanics applies to everything, including cats, then the math says the cat should be in superposition. The only way to get a definite outcome is to open the box and observe collapsing the wave function. Schrödinger created this thought experiment to show what he considered a fatal flaw in quantum mechanics. But instead, it became one of the most famous illustrations of the measurement problem. We still don't know where quantum behavior ends and classical certainty begins, or if such a boundary even exists. In 1957, a young physicist named Hugh Everett proposed a radical solution. What if the wave function never collapses? According to Everett's many worlds interpretation, every quantum measurement doesn't select one outcome from many possibilities. Instead, all possible outcomes actually occur, but in separate branching universes. When you measure an electron's position, the universe splits. In one branch, you find the electron here. In another branch, you find it there. Both branches are equally real, but they can't interact with each other after the split. You only experience one branch, the one you happen to be in, so it seems like the wave function collapsed to a single outcome. But actually, other versions of you in other branches experienced different outcomes. This sounds like science fiction, but many prominent physicists take it seriously. Sean Carroll, David Deutsch, and Max Tegmark are among the many worlds supporters. Why? Because it solves the measurement problem by eliminating the need for wave function collapse entirely. The Schrödinger equation, the fundamental equation of quantum mechanics, describes how quantum systems evolve, and if you follow that equation without adding any extra assumptions, you naturally end up with something that looks like many worlds. The Copenhagen interpretation requires an extra postulate, wave function collapse. Many worlds doesn't. It simply takes the math of quantum mechanics at face value and asks, what if this is literally what's happening, but many worlds creates its own deeply unsettling implications? If true, it means that every quantum event, every radioactive decay, every photon interaction, every electron measurement causes the universe to split into countless branches right now. As you read this, the universe is continuously branching into incomprehensibly vast numbers of parallel realities. In some branches, you put down your phone a second ago. In others, you keep reading. In some, you never clicked on this video. In others, you don't exist at all because your parents never met, or because some cosmic ray caused a different mutation in a distant ancestor. Everything that can happen does happen, just in different branches. The multiverse isn't infinite, but it's vast beyond comprehension, constantly branching at every quantum event across every particle in the observable universe. And here's what makes this truly terrifying. If many worlds is correct, then you can never truly die. This idea is called quantum immortality, and it emerges naturally from the many worlds interpretation. The reasoning goes like this. Consider a life or death quantum event. Let's say you're exposed to a radioactive source that has a 50% chance of killing you instantly. In the many worlds interpretation, the universe branches. In one branch, the atom decays and you die. In the other branch, it doesn't and you survive. But here's the key insight. You can only experience the branches where you're alive to experience anything. The branch where you die contains no conscious experience for you. So, from your subjective perspective, you always survive. No matter how many times you repeat the experiment, you always find yourself in a branch where you're alive. Extend this reasoning to every life-threatening situation, every near-miss accident, every illness, every danger. All these events have quantum components at their core. Whether a cancer cell forms, whether a neuron fires correctly, whether a cosmic ray mutates your DNA in a fatal way, these are all ultimately quantum events. If many worlds is true, then there are always branches where you survive. And since you can only experience the branches where you're conscious, you should subjectively expect to continue living indefinitely, always finding yourself on the improbable but existent survival branches. This idea was most thoroughly explored by physicist David Lewis in a posthumously published lecture. He argued that if many worlds is correct, the observer must expect with confidence to have eternal life despite any dangers. But, and this is where it becomes truly horrifying, Lewis pointed out that survival doesn't mean health or well-being. You might survive a fatal accident, but only as a severely injured version of yourself. You might survive cancer, but only by existing in a state of continuous suffering. Lewis compared it to the Greek myth of Tithonus, who was granted immortality but not eternal youth, doomed to age forever without dying. Max Tegmark disagreed with this grim forecast. He argued that real death almost never satisfies the conditions for quantum immortality. Death isn't usually an instantaneous quantum event. It's a gradual process. Your consciousness doesn't blink out all at once. Neurons shut down gradually. Your sense of self blurs and fades. And this gradual fading means there is no sharp branching point where some versions of you survive intact. Instead, the probability amplitude, the weight of existence of branches where you remain conscious, decreases steadily with each quantum choice. You become increasingly unlikely, your existence spreading thinner and thinner across the multiverse like a signal fading into noise. Most physicists, even those who accept many worlds, reject quantum immortality. Sean Carroll points out that when the universe branches, the different versions of you become distinct individuals. You can't privilege one branch as real you and ignore your death in other branches. If most versions of you die, then in any meaningful sense, you have died. The debate continues. But the very fact that we're having this conversation, that we're seriously discussing whether quantum mechanics implies you can never truly die, shows how radically quantum physics challenges our understanding of existence itself. If many worlds and quantum immortality seem strange, consider this. Some quantum experiments seem to suggest that the future can influence the past. This brings us to the quantum eraser experiment, a variant of the double-slit experiment that produces results so bizarre that they seem to violate causality itself. Remember the double-slit experiment. When you observe which slit a particle passes through, the interference pattern disappears. But what if you could erase that information after the particle has already passed through the slits? Here's how it works. Send photons through a double-slit setup, but mark them so you can tell which slit each one passed through. This destroys the interference pattern as expected. But now add a second step. After the photon has passed through the slits and is on its way to the detector, pass the which path information through quantum eraser, a device that scrambles or destroys that information so it becomes impossible to determine which path the photon took. The result? The interference pattern comes back. Think about what this means. The photon has already passed through the slits. It decided whether to behave like a wave, both paths, or a particle, one path, before the quantum eraser was even activated. Yet erasing the which path information after the fact seems to retroactively change the photon's behavior. It gets even stranger with the delayed choice quantum eraser. In this version, the decision to erase the which path information can be made after the photon has already hit the detector. The choice happens in the future relative to when the photon passed through the slits. Yet the pattern on the detector correlates perfectly with whether the information was erased or not. It's as if the photon knew in advance whether its which path information would be erased and adjusted its behavior accordingly, traveling as a wave, close-to a particle, based on a decision that hadn't been made yet. Now, before you panic completely, this doesn't allow for backwards communication or time travel in the traditional sense. You can only see the correlation between the eraser and the interference pattern after comparing data from both detectors. The signal isn't transmitted backwards in time, it's revealed through correlation, but this doesn't make it less unsettling. It suggests that quantum reality doesn't have the clear temporal structure we assume. Events aren't simply arranged in a chain where causes precede effects. Instead, quantum correlations can connect events in ways that transcend our normal notion of time's arrow. Some interpretations of quantum mechanics embrace this explicitly. The transactional interpretation proposed by John Cramer suggests that quantum interactions involve waves traveling both forward and backward in time, creating a handshake across time to establish correlations. Whether you accept this or not, the experimental results remain. The future and the past are entangled in quantum mechanics in ways that defy our intuitive understanding of causality. And we don't fully understand why or what it means. Perhaps the most famous quantum paradox involves entanglement, what Einstein called spooky action at a distance. Create a pair of entangled particles, photons, electrons. It doesn't matter. These particles are created together in such a way that their quantum states are correlated. If you measure one particle and find it in a particular state, the other particle will instantly be found in a corresponding state, no matter how far closet apart they are. Einstein hated this. In 1935, he and colleagues Boris Podolsky and Nathan Rosen published a famous paper arguing that quantum mechanics must be incomplete. They reasoned that if measuring one particle instantly affected the other particle light years away, information would have to travel faster than light, violating special relativity. Therefore, the particles must have predetermined properties, hidden variables that quantum mechanics simply doesn't describe. For decades, this seemed like a reasonable way out. Maybe particles aren't really in superposition. Maybe they have definite but hidden properties, and measurement just reveals what was already there. But in 1964, physicist John Stuart Bell proved that this couldn't be true. He derived a mathematical inequality that any theory based on hidden variables must satisfy. Then experiments could test whether nature violates Bell's inequality. And it does, decisively, repeatedly. The experiments show that entangled particles are genuinely in superposition until measured, and that measuring one really does instantly affect the other regardless of distance. The correlation isn't explained by hidden variables or pre-existing properties. It's a fundamental feature of quantum reality.